Hi there and welcome from Ventura, California to today's webinar, GNSS Jamming, Crowdsourcing Detection and Geolocation, sponsored by InsideGNSS and Roden Schwartz and hosted by WebAttract, the leaders in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they explore and compare the potential and current limitations of using smartphone density, ease of deployment, and signal utility against the capabilities of dedicated networks. You'll also have an opportunity to have your questions answered at the end and at the midpoint of today's presentation during our Ask the Expert panel session with all three of our panelists. Now, we've invited you along with over 430 professionals registered across 44 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher, InsideGNSS and Inside Unmanned Systems, would like to take a moment to welcome you and introduce our moderator for today's session. So over to you, Richard.
Thanks, Lori. On behalf of InsideGNSS and our sponsor, Roden Schwartz, I'd like to extend a warm welcome to our international audience for today's web seminar. We're delighted you could join us. Our moderator today is Demos Gebre-Egzieber. He's a professor of aerospace engineering and mechanics at the University of Minnesota. His research deals with the design of multi-sensor navigation and attitude determination systems for aerospace vehicles. And recently his work is focused on multi-sensor solutions for operations in GNSS stressed and GNSS denied environments. Demos, welcome today.
Thank you, Richard, and thank you everyone for joining us today for this exciting webinar. So this webinar is, all of you are here because you're interested in GNSS, and we know that GNSS, its position solution, has revolutionized road, rail, air, and marine transportation. The timing function of GNSSs are used as the heartbeat for clocks around the globe. And with technologies like PPP and RTK that are going to improve its accuracy even down to the centimeter level, being around the corner, it's going to truly revolutionize the way we do transportation. However, there's a fly in the ointment, and it's always been a fly in the ointment, and that's jamming and interference. Mitigating this threat has been the focus of intense research for quite a while, but the recent confluence and maturation of a set of interesting technologies is going to bring another tool to the fore to deal with this issue, and this is what today's webinar is all about. So if you're wondering what kind of technologies I'm talking about, that is going to be our first poll question, and to give you an idea what technologies we're talking about for this new approach. If you put up the first poll question, Lori.
Absolutely, and folks, coming up on the screen is that first poll question, and we'd like to know from each of you, what innovations are enabling GNSS jamming detection? In this case, you're welcome to select all that apply. Choices, as you see there on the screen: Internet of Things, network connectivity, multi-GNSS constellations, big data, raw GNSS measurements from cell phones. All right, looks like 42% saying Internet of Things, 55% network connectivity, 59% multi-GNSS constellations, 40% big data, and 80% raw GNSS measurements from cell phones. So, Demos, any thoughts about these responses?
Well, interesting. By the end of this webinar, you're probably going to have 100% on all of these categories, because all of these are interesting technologies that could probably bring a solution to this problem. So, with that, let's go ahead and get into the webinar itself, and let me introduce our first panelist. Our first panelist is Dr. Sherman Lowe, who's a senior research engineer at the Stanford University GPS Laboratory. His work focuses on navigation safety, security, and robustness. He was at Stanford. He has and was the associate investigator for the FAA evaluation of enhanced LORAN and alternative position navigation and timing systems for aviation, or APNT. He currently leads the work examining GNSS interference and spoofing detection and mitigation. He has over 100 conference, 20 journal, 14 magazine publications, and 8 U.S. issued patents on GNSS and GNSS-related technologies. Sherman holds a PhD from Stanford University and a bachelor degree from the University of Maryland, College Park. In addition to his research work at Stanford, he does teach some undergraduate classes at Stanford University. Sherman, welcome.
Thank you, Demos. Thank you, everyone. Good morning, good afternoon, or good evening, depending on where you are. I'd like to start this whole webinar by talking about localizing jammers using network and smartphones and bringing ideas that we've developed here, but also developed by other colleagues among the GNSS community. Let's start with the bottom line up front first, the points that we'll kind of cover. First is there are many ways to localize jammers, and really particularly with when we have network or crowdsourced observations. With smartphones and crowdsourced data, we'll gain a lot of advantages, particularly in terms of deployment, both because of its ease of deployment and also its lower cost compared to dedicated infrastructure. And because of that, they're a good complement for dedicated networks, but not necessarily a replacement. And we'll talk a little bit about that. Our focus here will be really on crowdsourced and network detection. It has a lot of applicability to different applications, not just consumer smartphones, but also, as we kind of mentioned in the poll question, Internet of Things, also aviation, automotive, and it can be used to not just help with jamming detection, but also in spoofing and other GNSS degradation detection. So let's start by looking at common ways to localize GNSS spoofing. The most basic way that kind of everybody has is omnidirectional detection, such as with a receiver or a dedicated device, and here's one that's shown up on the top right, that looks at incoming noise energy, either through changes in carrier to noise ratio or automatic gain control, which really kind of measures the incoming noise that is coming into our antenna. And so most GNSS receivers can do something like this. This is, of course, though, a coarse measurement and can only tell if we experience jamming. We can't really tell how close a jammer is. Either we might have a jammer that's weak and close by, or we might have a more powerful jammer that's a little further away. But it gives us a sense that there's a jammer in proximity. So a little stronger way of doing this is using angle of arrival or direction of arrival when we have an antenna or something that we can beam steer. And so on the bottom, we see an example of a product that does angle of arrival estimation of interference source. Both of these techniques are decent, but they only work best if we have measurements from multiple locations. And in fact, early jamming localization was done with a directional antenna and moving through different locations until we can finally find the jammer. And so, but if we have a network receiver, especially in multiple locations, we'll have many more localization techniques available. I listed quite a few here: proximity, angle of arrival, frequency difference arrival, a lot of different combinations of difference measurements that we can look at. And also we can use a combination of all of them to really lock in on where that interference source is. So the traditional way of doing a network is with some dedicated fixed infrastructure. They typically use high quality reference receivers with good antennas and monitoring equipment network together to cover a targeted facility or area. In this case, this is a cartoon shown of a system developed by Kronos and Harris or Axelis called Signal Sentry, and here it's shown kind of covering a port. And so this is kind of the traditional way of doing network-based interference detection. And with this way, there are lots of ways of doing localization. I'll emphasize two right now. I first start out with one of the most common ways is to use time difference arrival. And to do that, to use TDOA, we correlate the received noise of the interference source or other property from the interference source at each of our monitor sites. So let's say we have two monitor sites, Site 1 and Site 2. We'll monitor the interference source at those locations. And we'll correlate those characteristics together to find a time difference arrival of that property from the interference source. Of course, that generates a time difference arrival, which results in a hyperbolic line of position where that interference source might be located. And so this is our hyperbolic line of position. And so with two hyperbolic lines of positions, or three stations, basically, we can get horizontal position and localization of the interference source. Of course, this requires very good time synchronization between stations to be able to do this kind of localization. And but it provides a lot of capabilities. If the interference source is far away, those hyperbolic lines of positions asymptote to a given direction, so they, in some sense, it provides an angle of arrival if we only have two stations and the interference source is far away. The other technique we'll look at is power difference arrival, and while there are many other differences that we can use, we look at this one because this one is applicable to smartphones. Power, ideally in free space, falls as 1 over r squared, though really in the real world, that exponent can vary a lot in different environments. But regardless of what that exponent is, so it's, we'll just generally say it's 1 over r to the 2 beta. Regardless of what that exponent is, given the possible exponents, the ratio of the power that's seen between two stations will define a circular line of position where the interferer can lie. If we know that exponent, roughly know that exponent, we can then generate a circular line of position where that interference source should be relative to those two stations. And so the next slide, this slide shows that. And so we have two reference stations. If we kind of know, we make a power difference measurement, find that ratio, and know roughly what the power drop-off will be, we'll be able to find a circular line of position. With dedicated networks, we have, and quality monitoring equipment, again, a lot of these techniques can be employed, and frequency difference techniques and angle of arrival techniques can also be employed. We can combine all that and to get very precise localization. The great thing about these networks then is that they have high quality measurements. They're static, so we don't have to worry about figuring out their position, and they're generally trustworthy. We generally install them in and know what they're going to perform like. However, they're generally expensive. You need many monitoring sites to cover a given area. And here in this slide, we see an example deployment from Axelis for the 2014 Super Bowl. I know the 2019 one's coming up pretty soon. And this one has 5 stations just to cover an area of roughly a mile square, 1 kilometer squared. And so this is kind of the motivation for crowdsourced measurements, because with smartphones we can provide ubiquitous monitoring over a large area to supplement dedicated systems in locations where they're deployed, or to cover areas where dedicated systems would be cost prohibitive. So let's talk about the benefits of smartphone-based crowdsourced localization and RF and interference detection. We have ubiquity, of course. We have lots of users. Smartphone has in the world is 60 or 70% penetration. In the U.S. is a very high penetration rate. It's low cost. It's relatively easy to deploy. We can deploy it with just an app. In fact, we've developed an app based on the open source GNSS logger developed by Google, which Frank will talk about in the next talk. So we developed an app based on that to do that. And then improved capabilities can be done with either upgrading this app or upgrading the server, or both. And so it's reasonably easy to upgrade as well. And it also, now with Android, we have many metrics that we can get. Prior to Android 7, we have position, satellite, and carrier to noise ratio, CETA and NOT. But now after Android 7, we have pseudo range and pseudo range rate. We have automatic gain control measurements with Android 8 onwards. And so these measurements are good for doing some localization of jamming. And then and additionally, measurements like pseudo range and pseudo range rate, and AHC could also help with spoof detection as well. So these new capabilities of Android provides us a lot of power in helping detect any disruption concern for GNSS. And of course, the final thing is smartphones are networked. That's their reason for being. So it's already built right in. So if we want to compile the data from lots of different smartphones and process them locally, the capability is already built in. Studying crowdsourced interference detection has applicability to other realms. Any application with widely deployed GNSS receivers can use this technique. So we talked about Internet of Things. We can use them for aviation. Almost all commercial aircraft carry a GNSS receiver, and they should by 2020 with the ADS-B mandate. Automobiles, of course. So what we learn with smartphones and crowdsourced smartphone GNSS spoof detection and interference detection, we can apply to these applications. Aviation already mandates sending information about aircraft GNSS derived positions, and receive them from the ground with something called ADSB, which is automatic dependent surveillance broadcast. And so that's what's being transmitted. And so these crowdsourced reports from aircraft, for example, can be used to help quickly identify GNSS problem areas for aviation. Indeed, that's actually what's being done right now. Duchette and Barrett from Eurocontrol presented on using ADSB reports to localize interference. With this effort, they're taking ADSB reports, using that to generate a heat map of where GNSS interference may be. This plot that's shown here is from their presentation. It shows a heat map over Nicosia, Cyprus airspace, which is pretty close to Syria, so you understand why it's there might be jamming. And so they generate this heat map on the right of where jamming might occur. Hold on. Okay, there we go. We're back. And so that can be used to inform the aircraft to avoid those regions. This may be further improved with a proposal to add a few bits about power with using CETA and NOT measurements to this report, and this is something that's is being discussed. And so one can imagine similar concepts with automated cars, for example, or Internet of Things devices, and of course with smartphones. But we should remember that smartphones are not, they don't do everything that a dedicated network can do. They have several limitations that we need to be cognizant of. First, they're not homogeneous. They generally and because of various reasons, we'll generally have less confidence in these measurements than those from a dedicated network. They're not homogeneous. The users are often moving around inside buildings, outside buildings, being blocked, being under trees and other things, and they're generally not, and so they're not generally not in a controlled environment. They're often noisier, and the quality is not reference quality grade, particularly given the antennas inside the smartphones. And of course, the source may not be known or verifiably trusted. We also have fewer measurements available. And they're not available at very high rates. GNSS data is usually output at about 1 hertz on smartphones. And so this resolution, along with duty cycling, where the phone is not, the GPS part of the phone is not always operating, makes synchronization limited. So we can't get very necessarily precise synchronization of measurements between phones, not because not because they don't have a good time, but because of the output rates and when the measurements are being made. And as a result, these first three things, concepts such as time difference arrival, aren't currently supported by smartphones. Finally, of course, their coverage is ad hoc. So because of this, our major means of localization with smartphones is with proximity, and with we're just looking at which receivers are affected, and power. But we can overcome a lot of these limitations because of the quantity of smartphones we have. So it's often been said quantity has a quality all of its own, and this is really the power of the smartphone and crowdsourced device, that we can deploy a lot and have a high density deployment, which can make it quite effective. So we did some field tests. We did some field tests of smartphones using our app in 2017 through a couple of different jamming exercises. We have 15 different Android smartphones. Most of them were of various grades, but they were generally operating on Android 7.0 or lower. As a result, they didn't have AGC. Actually, AGC didn't come out until the fall of 2017, so there was no phones actually available with that. We tested mostly with looking at proximity and using CETA and NOT. There are several different jamming tests we were involved in, some using a PPD style, a personal privacy style jammer, so low power jammer on a car, and so it was a moving interference test, and another with a high power static jammer. We used our open source, our app based on the open source Google GNSS Logger app, and we had a backend server for processing. So let's look at some of the tests that we did, and so just to kind of examine what some of the challenges that I mentioned. And so here we're examining power measurements, in this case CETA and NOT, for interference detection. Here we see one of the challenges I mentioned, sorting out the noisy measurements. The top three plots, the plots show the average CETA and NOT of the top 4 GPS satellites as measured by each smartphone. So each plot shows a different smartphone. The top 3 ones are static smartphones that were sitting outside, and the bottom one is a dynamic smartphone. This is during a high-power jamming test, but the jammer was 30 kilometers away on the ground over the horizon, so you intermittently would see it in when it was turned on. And so what you can see with the static ones is they're reasonably consistent, and you can see a common drop, but amongst them when the jammer is turned on at about a little bit before second 3000. But with the dynamic one, because the user is walking behind a building, actually the user sometimes walk inside a building, we get a lot of drops instead, not just because of our natural movement. And so we need to be able to filter out the noise that are caused by the user and the environment from actual interference sources. And that's where we're going to leverage the power of the fact that we have lots of measurements and look for correlations like this one seen about time 3000 to detect those faults, those interferences, those drops that are due to actual interference and not local phenomenon that's happening within the phone or close to the phone. AGC can improve the performance, help sort out some of the uncertainty in the CETA and NOT. For example, when we walk inside a building, CETA and NOT might drop, but AGC may not. But you got to remember, a phone it is and operates in a noisy radio frequency environment, and there will also be quite a bit of natural variation, and so there will be quite a bit of natural variation in these measurements. Frank will show some next, but here's an example where we left the phone sitting idle in the outdoor courtyard, and there's some small variation where the AGC occasionally changes, but in the middle we have a drop of about 4 dBs, and this is a phone just sitting idly outside. So proximity and power are really the most powerful, useful ways that we'll use to figure out and localize interference. And so here's an example of a test that we did at a test site where we deployed 15 different smartphones, and these are in different colors here. And this is with a mobile low power jammer that drives a route that starts at the start point, goes out, goes in this triangle, and then comes right back. And we'll see how these smartphones can use CETA and NOT to detect. First slide, what we'll see is each smartphone is represented by a circle divided in half into hemispheres. The left hemisphere basically indicates the average CETA and NOT of the top 4 GPS satellites, and the right hemisphere indicates the average CETA and NOT of the top 4 GLONASS satellites. The interference source mostly affected GNSS, but GPS, but it also leaked into GLONASS. But we can use both. And the darker the color is, the lower the CETA and NOT is. So if we have a dark source, we know it's seeing more interference. And so in slide 1 here, we see that the jammer is at the starting point. A few of the smartphones don't see it because they're a little bit over the hill, and so that jamming source is blocked a little bit. And then so as the vehicle starts driving, now the smartphones along the route start experiencing jamming. So now it's gotten to this third point. As we go down, we'll get to the intersection. The smartphones indicate the jammer's at the intersection. It's a little bit past the intersection. It's at the turn. It's a little bit past that. Now it's at the furthest end of the route. Now it's on its way back to the intersection, and then back to the starting point. And so you can see that just having that density really allows us to have decent localization. In this case, we didn't even use the difference or the ratio of powers between the phones for doing that, and that's something we'll look at later. And so again, just the key takeaways: dedicated network solutions provide many ways to rapidly localize an interference source. Crowdsourced smartphones are useful in its ease and density of deployment. We can detect interference with these resources, and particularly for areas that aren't covered by dedicated networks, but they're also a good complement to dedicated networks, which Stefan will talk about, by extending the coverage of networked or sparsely deployed trusted receivers. Smartphones can also provide proximity and power measurements for localization, and they can also help with spoof detection. So with that, back to you, Demos. Thank you very much.
Thank you, Sherman. All right, so moving on, let me introduce our next panelist. And our next panelist is Frank van Diggelen, who is the principal engineer in the Android location team at Google, leading their high accuracy location services, including Wi-Fi and GPS. Previously, he was a fellow and a vice president of Broadcom, where he pioneered techniques that allow GPS to work in cell phones. He holds over 90 U.S. patents on GPS and is the author of the textbook, or the book, AGPS, the first textbook on assisted GPS. Frank holds a PhD from Cambridge University and a bachelor degree from Witwatersrand University in South Africa. He is a fellow of the Institute of Navigation in the United States and the Royal Institute of Navigation in the United Kingdom. In addition to all the stuff he does, he also teaches a GPS class at Stanford University. Frank?
Thank you, Demas. Hello, everybody. I'm going to talk to you in more detail about the Android GNSS measurements that Sherman mentioned several times in his talk. And as Sherman showed us with those nice little coffee beans driving down the road, you can use carrier-to-noise density ratio to detect jamming, but CN0, or carrier-to-noise density, varies for many reasons, and the most common of which is that you might walk from outdoors to indoors. And as Sherman mentioned, there's another signal that is available called AGC, or automatic gain control. So I'm going to discuss the concept of gain control and then go into details about how you access it. So this slide that you're looking at shows the kind of dial you may have seen on a stereo or a voice recorder. If you're recording sound and the input is too large, then the recording will lose fidelity because the input gets saturated, and you see this when that dial is way over on the right in the red. And so to control this on sound recorders, you typically have a button down the bottom there, as you see, labeled gain control. And you turn this down and get the needle to bounce around in the middle. So GNSS receivers are exactly the same. They measure the total input power at the front end, and if it's too large, they have automatic gain control to reduce the power to appropriate levels. So I'm going to show you how to access this automatic gain control and how to use it to detect jamming. So this slide shows you the page that you want to go to find the API describing the Android GNSS measurements. So how do you find this page? Well, I'll give you a pro tip and tell you how we do it inside Google. We go to a Google search bar and type in something like Android GNSS measurements API, as you see on the right here. And one of those two top links will take you to this page. So any kind of terms like that in the search bar will typically find you the right page, and then, as I said, that's how we do it internally. A little added bonus here, as when I tested this to make these slides, the third link shows an article that we did in InsideGNSS magazine about the tools to work with these measurements. So you find these measurements, and the one of interest is GNSS measurement. If you go click on it, you'll discover the different methods supported here, and one of them is get CN0 dB hertz. So that's how you get the carrier to noise density ratio that Sherman's been talking about. And as I mentioned, jamming will make this go down because jamming increases the noise density, the N0, and so a jammer will decrease CN0. But as we mentioned, walking indoors, putting your phone in your pocket, that will also decrease CN0. So what we want to know is, has CN0 gone down because the N0 has gone up, not because the carrier signal has got weaker. So to know if the N0 has gone up, we want the automatic gain control. And you'll find that in this API as well. It's a method called get automatic gain control. And there's a brief description there, and the important part is the bottom, where it says, in cases of strong jamming in the band of the signal of GNSS, this value will go more negative. So think of that dial I showed you on the first slide. If the energies or the power, input power is getting too large, the AGC is automatically turning the dial down. So the value you'd read here goes negative. So negative values of automatic gain control indicate that the presence of jamming. So now let's see how this works in some experiments. So the experiment done here, this is, as I describe this, you might get the feel you're watching a cooking show, because the way you can test this very easily with a phone is just to take a microwave oven, put a cup of water inside it and switch it on. And that's exactly what we did here. And what we're monitoring, we're logging the automatic gain control field that I just described. And ordinarily, so at this stage, the microwave is off, and you'll notice this field bounces around a little bit up and down, depending on the ambient interference that's present at the front end. And at this stage, the microwave was switched on, the phone was in front of the microwave, and you see the automatic gain control adjust down, and then the phone was placed right at the crack in the door, the edge of the door there, and you see it jump down quite a lot more, down to about 15 dB down. So a colleague of mine did this experiment and has shown this in some presentations before. I thought if I'm talking about it, I should try it out myself. And I did. This took all of about 2 minutes. And so once I show you how to get access to these measurements, I encourage all of you to try it yourself. So this was a different microwave oven. This was my one at home. Microwave off here, microwave on, phone in front of the door. Not much happening there, which meant I have quite a nice shield on my microwave. But then microwave at the door edge, and I see it jump down to maybe 10 dB lower than what it was when the microwave's off, and then switch off the microwave and the signal goes back up there. So as you can see, you can test the presence of some interference with something so little as the leakage that you might get from your own microwave oven. So before we carry on, I just want to give you some insight into the kind of energies we're talking about here, the kind of power. So as you may know, the GPS signal is itself well below the noise floor in a GNSS receiver. So here is the noise floor in the 2 megahertz bandwidth. The nut is minus 111 dBm, and the GPS signal when you're outdoors is well below that, something like 20 times below that, and in a cell phone it's another 5 times or so below what it would be with a patch antenna. So the GPS signal itself is well below the noise floor, and what we just demonstrated is that we measured leakage from the microwave oven at about 10 times higher than the thermal noise floor present in a GNSS receiver. So a couple of things to notice from this is, first, don't panic about what your microwaves might be doing to you. That energy is still very, very low. Down the bottom here, you see some of these tiny numbers, which maybe you didn't even know, some of these prefixes like femto, atto, and zepto. These are tiny values we're talking about. And so the leakage in the L1 band from the microwave is still at 1,000 times lower than the energy you're experiencing right now from any Wi-Fi network around you. So nothing to worry about from your personal point of view, but from the point of view of GPS, it does show how easy it is to jam GPS. If you have any kind of signal in the L1 bandwidth, you can jam it. So for example, some of you may be asking, well, why doesn't Wi-Fi jam GPS as well? It's because this 100 picowatts or minus 70 dBm is the Wi-Fi signal in the Wi-Fi band, i.e. 2.4 gigahertz or 5 gigahertz, and it's not the signal in the L1 band of GNSS. However, if someone were to transmit almost anything with very weak signals in the GNSS band, as you can see here, they could very easily swamp the noise level and the GPS signal itself in GNSS, hence this webinar and hence the AGC for detecting that. And so with that, back to Demos.
Right. Thank you, Frank. So at this point, we'll take a short pause and do a Q&A from the answer some questions that some of the audience have asked. So with that, let me start off with the first question, and this one is for you, Sherman. And the question is, how can actual jamming signals be extracted from natural signals that may have a similar pattern in what you're seeing? For example, C over N naught degradation, AGC differences, and ranging errors all can be caused by things other than GNSS jamming. And I think you said a little bit about it, but if you can add a little bit more to that, that would be great.
Sure. So the question is, how can we extract basically jamming from natural sources that would cause degradation in our AGC or CDNOM measurement. And really the idea here is to use the fact that we have a lot of multiple smartphones, and then we're going to try to that jamming, hopefully if it's a wide area jamming, will be seen by multiple smartphones simultaneously. And so we're going to look for time correlations between these measurements, whereas natural environments or natural changes are things that are happening specifically to a given user, and so they shouldn't be correlated from smartphone to smartphone. So that's really the way we're gonna use it. If there is a dedicated network nearby or a trusted receiver, we can use that. We can leverage the fact that we trust that a little bit more, and that it's in a more controlled environment to do the detection as well. So those are kind of two basic ways we would use to to separate out natural changes from jamming and other deliberate degradation.
Thanks, Sherman. Frank, do you want to add anything to that, or?
No, that was good.
Great. All right. All right. Let's see. Next question. This one is well, I think you answered, but this one is for Frank, and I think you've kind of answered along the way. But I'll ask it again. It's how often is GNSS interference a problem? In other words, are we finding a solution for a problem that it doesn't exist, or is it actually a problem?
Okay, well, this is Frank. I think I can answer this and another question about how often this happens from the cell phone itself at the same time. So how often is GNSS interference a problem? The answer is seldom, but significantly. And if you just go and search for GNSS jamming, you'll discover some fairly dramatic examples that have happened fairly seldom, like maybe once a year something dramatic happens, but very dramatic. Like, for example, an entire GNSS in an entire town can be taken out. One famous example or notorious example was the U.S. Navy was doing exercises off the coast of San Diego, and one ship was jamming another to test the robustness of the second ship. Unfortunately, beyond the second ship was the city of San Diego. The entire town had its GNSS jammed. The cell phone network stopped working. So very dramatic example. And there's other ones equally worrying. People buy jammers to stop GNSS tracking systems from working in things like trucks. And some of these have taken out or have jammed the GNSS LARS system that supports landing at airports, so as the trucks have driven by. So fairly dramatic cases occasionally. In the phone itself, there are some bands that interfere with GPS, but the phone designers usually know about that, so that will affect the phone. That will show up in the AGC, but it happens quite rarely and usually in a controlled manner.
Okay. Sherman, do you want to add something to that from an aviation point of view? This is a frequent issue, or is it a really infrequent but very critical issue?
Sure, I'll add something to that. What we do monitor drops in AGC from the WASP reference stations, and we do see, depending on the location such as Miami, which is near a highway and a busy thoroughfare, we see multiple occurrences throughout a week. We might see 30, 40, 50 occurrences throughout the week, and so we do know it's happening. It happens a bit. How many people get affected, it's not clear, and how critically that affects our infrastructure, that's not clear. What we have seen in the last couple of years is that has leveled off in the U.S., partly because of regulations and laws, and partly because we've started trying to ban the sales of these PPD devices. But we still get reasonable amounts of events. I think Europe is doing a similar monitoring and testing of how often they have interference events, and I think theirs is, at least in one of the countries, is still going up. Stefan might know a little bit more about that. So these events, kind of like as Frank said, are rare, but not, and big events that make the news are pretty rare, but they're not as rare as you think. Like I said, multiple times in a week, as seen in each of our WASP reference stations.
Okay, so the audience is sending in lots and lots of questions, and thank you. Keep on doing that. But let's do a quick poll. Thank you, Lori, for setting up that poll. Let's do a second poll question and move on to the second half.
Right. Quick poll before we pass it back to Frank, and that is a question here regarding interference detection apps. And in this case, as well, is select all that apply. Responses are, I'm involved in developing such an app. I'd use one to monitor GNSS interference on my device. I'd use one to enable crowdsourced detection and location of a jammer, or I would not use such an app. Looks like 14% involved in developing such an app, 64% saying I'd use one to monitor GNSS interference on my device, 58% saying I'd use one to enable crowdsourced detection or location of a jammer, and 9% saying I would not use such an app. Demos, any thoughts here?
9% is kind of interesting. But anyway, all right. So our next, Frank and then our next panelists will say something more about such apps and how they would be put together. So with that, let me hand it back to you, Frank, for the second half of your presentation.
Thank you, Demos. So now I hope some of you are asking, well, how can I get access to these measurements? And so that's what I'm going to show you now. So the first question is, well, which phones support GNSS raw measurements? The short answer is all new high-end smartphones. But if you want to know specifically, we maintain this page. There's a URL there, or you can find it the same way I described before. If you just search in the search bar for Android raw measurements, and you'll find this page where we have a table. So it's a manually maintained table where every Android phone that we know about that supports raw measurements is listed. They're listed in order of newest first, not alphabetical. So the most new phone that we know of goes at the top. And so you'll see from this micro print that the table has got quite long now over the course of a couple of years. And then there's some details in the table, and in particularly automatic gain control. This field itself was only added in the last year. When we first defined the API for the raw measurements, automatic gain control was not included, simply because we hadn't thought about it. And the first time we did a public tutorial explaining the raw measurements and their use, we had representatives from about 5 different government agencies come up to us afterwards and ask and say, why don't you have automatic gain control, and can you please add it? And so we did. And it's in there now. And so because it was a late edition, it's not in all the phones that are out there right now, but it is in some. I've highlighted a couple of phones there that support it. And so if you want to play around with this field, look at this table and see which phone supports the kind of measurements you want. Now, if you're going to write an app to make use of this, you want to know this programmatically. And so the question, does the phone support GNSS measurements, can be answered programmatically by using this method onStatusChanged, which returns this value, GNSS measurement status, and it has 3 values. It can take on 3 values. One is that the measurements themselves are not supported, so typically this will be true of older phones, and then of course you can't get anything. You can't get the automatic gain control, to be precise, or any other raw measurements. Another one is that the measurements may be supported, but the user has location off, in which case you can't get the raw measurements. And then the third one is what you need to see to be able to proceed. You need that the measurements to be supported, and you need the user to have turned location on. So you'll see status ready. I'm going to talk more in a little bit about getting permissions from the user to access location. So, but just for now, you'd need that field to be on to proceed. And then you'd want an app that logs the data. Well, if to play around, you can just start with Google's own GNSS Logger app, which is available on GitHub. And if you're writing your own app, then you should also start there, because this app, all the source code is available on GitHub. So start with our app, and you can just copy the source code and see how you use it to get hold of the CN0 and the AGC, and possibly the location of the device if you want to do crowdsourced location of jammers. So now the location that you want is the one from the fused location provider. So what is that? I'm going to describe that now. So inside Android, there are three different ways you can ask for location. You can ask for the GPS location provider, which will provide you location from GNSS, or you can ask for the network location provider, which will provide location either from cell tower or Wi-Fi. And then the fused location provider is what it sounds like. It is code inside Android that fuses these two and provides the best possible location available at any time. And so that's called the fused location provider. So anytime you want to get a location, fused location provider is the best one to get, because it should always provide you the most recent and most accurate of the available locations. Now, when you go and look at these descriptions of location providers, you'll find this blue box online that describes the permissions that you need. And so you have to have permission from the user. If you write an app that requests these locations, it won't work. You won't get the locations unless you have location permission. And so when you write the app, you should ask for location permission and explain to people how you're using it and what you're doing with it. So in summary, if you're building a jammer detection app, you should start with the GNSS logger open source code, use both CN0 and AGC values in a way that Sherman and I have presented. You must have user permission, and specifically you must have this one called access find location. And if you want to get the FLP location, you similarly need the same permission. And so just a few things to talk about if you are making apps. You must have user trust. If the user doesn't trust your app, they'll simply delete it. So when you ask for permission, you must have full transparency. Explain to the user what you're doing. You should be all of this. If you're using location to crowdsource the source of a jammer, then you should be keeping everything should be anonymous. You should explain that to the user, and you should explain that they have control. They should be able to revoke permissions easily, and you should explain that so then that they trust your app. Also, battery life is very important. You should explain to the user how you're using the battery, and you have some choices here. And one of the choices is that you don't have to switch on the GPS to monitor it. A good idea is to run your app in background mode and set it up as a passive listener, so that when some other app is using the GPS, for example, someone's got Google Maps open, then only at that stage can your app run. And so you can set it up like that. So if you just if you Google's terms such as passive location listener, you can find a lot of discussion online about how to do this. And that way you can achieve what you want to achieve, because you of course would be protecting the user when they're using location anyway, but you're not running not using up the battery by invoking the GNSS receiver yourself. And another thing to think about is periodicity. How often do you want to do any updates or monitoring? So keep that in mind. And then finally, if you're making an app, keep in mind that sooner or later something will go wrong, and if one of these location providers is not available, GNSS or NLP, FLP should always provide the other. So that's why we want you to use FLP. And if your app itself crashes, you should have some graceful crash recovery. So keep these three things in mind when you're making apps, and build great apps. And with that, back to you, Demos.
Thank you, Frank. All right, so let's move on, and let me introduce our last panelist, who's Stefan Meyer, who's a Senior Development Engineer and Project Lead, Location-Based Services Lab at Rohde & Schwarz. Stefan works in the Test and Measurement Division of RNS. His focus is on E911 positioning tests for mobile phones. He developed a 3GPP compliant ESMLC, which fuses assisted GNSS and Wi-Fi measurements. He holds 2 U.S. patents in the field of navigation and received his Bachelor of Science or Diploma of Engineering in Electrical and Communications Engineering from the Technical University of Munich. With that, I'll hand it over to you, Stefan.
Thanks, Demos, for the kind introduction. and welcome from my side as well. So my topic of my slides is standardization of crowdsourced GNSS jammer detection. So when I heard about the topic of this webinar, I thought actually this topic has been around for quite some time. I think it's been around since almost 10 years that crowdsourcing of smartphones could actually help tracing down jammers. Nevertheless, it didn't become a reality so far. And I think there were several essential parts missing, and that has to do with standards and standardized APIs. And I think in the recent years, in the recent 2 years, two major stepping stones became available that now enable us or pave the way to such a crowdsourced GNSS jammer detection application. So on the right side you see, for example, a mock-up how it could look like one day. So all the people, all the users of smartphones in the city of Miami could contribute and immediately identify jammers here. So going back to the major stepping stones, I think the major first stepping stone is kind of obvious. It's the Android 8.0, which opened up its API to access the raw measurements of the GPS receivers inside the smartphones. So before that, it was simply impossible for app developers to access such raw information. And I think this is one of the key enablers. And this is available, as Frank pointed out, since August 2017. And thanks to Frank and his team, now every app developer can actually write a smartphone app that can detect GNSS jammers, which is a quite significant advancement in my eyes. A second stepping stone, which is less prominent in my eyes, is the standardization of threat reporting. So there was recently a European Union project to standardize how threats can be reported to a centralized database. So multiple sources can actually work together, contribute together to a single crowdsourcing database. And this also became available in November 2017. And in the following slides, I would like to talk a little bit about those two stepping stones and how they could pave the way for our vision for jammer detection. So regarding the first stepping stone, of course, I don't want to lose too many words. Frank already gave a perfect presentation about that. But just to give you motivation, when you look at the picture, I try to mark a few of the people, but it's probably not even a third of the people on the picture. And if only that fraction of smartphone users would contribute to such a crowdsourcing network, we would have a super dense RF monitoring network. And the density is that single big advantage of the crowdsourcing, as Sherman pointed out. So such a density of the monitoring network is simply not realistically possible with professional monitoring networks. So you probably cannot afford putting an RF monitoring station every 100 meters from each other. And I will explain in the next slide why this is actually beneficial to have such a density. But first, I would like to talk about the stepping stone number 2, the standard for threat reporting. So this was developed as part of a European Union project, Strike 3, and they published a standard that is openly available in the internet. It's currently just a draft, but I expect that it's going to be turned final in the next month. And that standard codifies which information RF monitoring network should provide to a central database to report a jamming event. So it's actually intended not for smartphones, but it's intended for professional RF monitoring network. So something like you see on the right side. So here you see a picture of my hometown, a map of it, and a typical deployment of a RF monitoring network. So it's a pretty dense deployment, but it's 9 stations for, I would say, an area that covers a population of maybe 700,000 people. So this is a network that can easily detect higher power jammers. So higher power jammer is not a problem at all, and it can probably be traced down fairly easily. But if you have a very low power jammer, like the personal privacy devices, which are of course illegal in Europe and also in the US, but somehow always someone gets hands on such a device, and those devices might emit only at a very low power. So they are just jamming maybe a radius of 150 meters or something like that, and it's very hard to trace such a device. So this is where crowdsourcing could actually be a perfect augmentation of professional RF monitoring networks. By the way, because I think it was asked before, this Strike 3 project is also publishing regularly their observations. They're running such a threat collection server already, and they're regularly collecting and publishing the trend lines of jamming incidents. So if you're interested how the number of jamming incidents is evolving in Europe, you can look it up at that webpage. They've got a pretty decent presentation about that. Well, we have now these two worlds. We have the world of professional RF monitoring networks and this JAMA database that is made available by Strike 3 and that is used by regulators. And on the other end, we have a highly dynamic, different world, which is consisting of smartphones and apps. And everyone can write an app, but not every app developer can actually contribute to this JAMA database. So this JAMA database is only accessible by professional monitoring networks. So not everyone can file jamming reports in this database. And the question is now, can we somehow get these two worlds together? Can we somehow manage that app developers can also contribute to such a monitoring solution? And in my eyes, it's not as simple as drawing a line here from the app to the JAMA database, because the JAMA database expects that it knows whom it's talking to, and only, let's say, authorized monitoring networks can contribute. So what is missing in my eyes is some intermediate entity that I call here a standardized virtual RF monitoring network. And that one could act in between the app and the JAMA database. So towards the JAMA database, it could actually have the same interface as a regular RF monitoring network. So for example, this Strike 3 interface that I talked about. So it could look like yet another RF monitoring network towards the database. And towards the application, it could act as an entity that anonymizes data and collects and verifies the crowdsourcing information. So this entity could actually fulfill two of the challenges. So one challenge is actually the privacy, to take care of the privacy of the app users. And the second one is to take care of the integrity of the measurements, to avoid abuse, that someone is filling the database with bogus reports. And last but not least, it's also removing some obstacle from the app developer. So the app developer doesn't have to run his own backend server. So if someone wants to contribute, he can simply add that functionality in his app and send the reports over the standardized, potentially standardized interface towards such a virtual RF monitoring network. Now let's have a look how this could be looking like from a more technical perspective. So essentially this is pretty much the same picture. You have the central database that is keeping track of jamming events. And then you have regulators or police or air traffic control that can access that database to trace down jammers. And this database is traditionally filled from professional RF monitoring networks. RNS also has such a RF monitoring solution which is called RNS Argus. And that one is operating monitoring stations and contributing data to such a database. And our virtual network could fit in just next to that monitoring solution, this professional monitoring solution. So here again, we have the same interface, which could be the Strike 3 interface. And on the low end, we have the GNSS receivers built in smartphones that provide the raw measurements over the Android API to various apps. And this is where I have the feeling there might be some missing link, because how would an app actually report its findings, its measurement of a jammer to a common database? So I think the real power is actually if many apps and many users are contributing. And this could be a potential candidate for standardization. For the sake of completeness, there is also another variant how crowdsourcing could be enabled. And this is by using a 3GPP standard. So 3GPP is a standardization body that standardizes LTE and 5G radio access technologies. And they already have a crowdsourcing solution, but not for JAMA detection. So they offer a crowdsourcing solution to operators, and that is measuring the coverage of the mobile network. So technically, this could also be extended to also cover JAMA detection. But this at the moment is not the case. So this would require certain effort at standardization and a certain time. So this is why I don't focus on this presentation on this approach. I think the viable solution for right now is actually based on apps and the Android API. Now, a short excursion talking about crowdsourcing. I think this is also an area where legal aspects and privacy might come into the picture. So the global nature of crowdsourcing is also a challenge, because this JAMA detection mechanism we're talking about might be regulated in some jurisdictions. So I'm not a legal expert, but I could imagine that it might be somehow regulated. And on the other hand, the privacy regulations in different regions are also different. So besides the plain technical specification how an app could report such measurement to a database, a standard could also give guidelines to app developers how to take into account those legal and privacy implications. So for example, it could give some framework or some rough idea what an app developer should actually care about and look into. One example is, for example, we could allow the user not to participate at all, to participate only in a completely anonymous fashion, or if the user consents, the user could also participate in an authenticated way. By authenticated way, I mean the user could send user ID along with the jamming report. So you might ask now, why can't we do that completely anonymously? So isn't anonymous reporting completely sufficient? And my thoughts here are, maybe yes, maybe it is completely sufficient to allow only anonymous reporting. Nevertheless, if some certain fraction of the users would actually send their user ID along with the jamming report, this could help the crowdsourcing algorithm to easily identify incorrect reports. But it's not it doesn't have to be a requirement. It could also be, if you have a very clever crowdsourcing algorithm, that you can also filter out by the sheer amount of jamming reports. With a clever algorithm, you might be able to filter out outliers, incorrect devices that have a broken GPS receiver, or even ill-intended or bad-intended attacks. So this user authentication is a plain optional thing that is not a mandatory thing for crowdsourced jamming detection. Well, to summarize, I think I wanted to present you some standards in the field of crowdsourcing jamming detection, or standard interfaces. And I think those interfaces help us a lot to advance the idea of crowdsourced jammer detection. I have the feeling that there might be some small gap in between, and this is the link between an app and a virtual RF monitoring network. So this could be a potential candidate for standardization, and this is also why I wanted to bring it up in this webinar. So maybe if the GNSS community here in the audience is interested in such a standard, I would be very interested if there's a drive for that. And then we could actually bring that up in a standardization body, for example, in ETSI, and specify the way how apps could report jamming events. So a blueprint for that one could be this ELS AML standard that is specified currently in ETSI TS 103.625. And this is used for emergency caller location. And they specify a simple HTTPS post message that carries the position of someone who calls an emergency call. And in a similar fashion, one could codify the way the app reports, and such a report could actually contain the minimum data set that is already identified in the Strike 3 standard. And such a data set would be consisting of some event definition, so some information: did the app detect the event because of some AGC measurement or because of some C/N null observation? Which frequency band was affected by the jammer? What was the region where the jamming was observed? So this could, for example, be derived from the fused location provider in case GPS is not available. The date and time of the jamming event. Potentially a delta power, so if that one is available, this could give the crowdsourcing algorithm some better idea how strong the impact is, or how far the jammer is away from the observation. And as I said, only if the user voluntarily consents, the user could also convey some kind of user token ID to authenticate his report. But this is completely optional. And I think if we only manage to get some amount of apps reporting completely anonymously to a database, it would be a big leap forward in our goal to avoid or to counteract the spread of jammers. Well, that's it from my side, and I'm looking forward to your input, and I give back to Demos. Thank you.
All right, thank you, Stefan. All right, so before we head on off to our last Q&A session, just a couple of more things I'd like to say. So if you need further information, here is a link to Roden Schwartz, a webpage from them, and in addition, we've given you contact info to our panelists or their organizations, so you could reach out to them or look at this link to get more information on the topic for today's webinar. All right, let's see. So before we head off to our last Q&A session, let's do one more poll. Lori, if you could bring up the poll question.
Absolutely. On your screen there, poll 3, what is your level of concern about the impact of GNSS jamming? Options here, level of current jamming does not warrant the investment. Jamming is only a localized issue near critical infrastructure. GNSS jamming is a critical concern that warrants investment. A cost-effective and proportional solution is critical. I've got 2% saying level of current jamming does not warrant the investment. 17% jamming is only a localized issue near critical infrastructure. 43% saying GNSS jamming is a critical concern that warrants investment, and 39% a cost-effective and proportional solution is critical. Any thoughts here, Demos?
Well, the fact that the last two selections got the most input underlies the importance of this webinar that we've put together today, so that's nice to see. All right, so with that, let's move on to Q&A, and thanks to the audience, there's a lot of interesting questions that have come in. So let's start off. In the first one, I am going to give it to you, Stefan, and the question is, what is the maturity of the virtual jamming detection network shown on one of your slides? Does this network already exist, or does it have to be created, or where do things stand?
Mm-hmm. Okay, basically for professional RF monitoring equipment, this Strike 3 server is already running and live. I think it's running as part of a demonstration project. I'm not sure how long that's going to be maintained after this European Union project is finalized, but this one is already up and running. This intermediate entity that collects the measurements from smartphones is just a concept. So this one is not built, not developed, but it's a concept that could become realized if there is demand from the GNSS community.
Right, thank you. Let's see. This next question is for, let's see, this one is for you, Frank. It had to do with a detail on one of the slides you showed. It says, can you explain the 3 dB toggle that was seen before the microwave was turned on? That was before any jamming sources were active.
Right. So yes, that, as everyone will probably remember, the slide where there was a picture of the microwave oven, and then before the microwave was turned on, you saw the line going down and up over about 3 dB. This is normal for the AGC, because you remember that the AGC is responding normally to noise. The GNSS signal is below the noise, and so there'll be some natural fluctuation. And if you're building an app to make use of the AGC, you should get some calibration around this natural fluctuation and be aware of what is just ordinary noise that the AGC is responding to and what is real jamming. So summary is that was just the ordinary variation in the noise, and the AGC doing its best to maintain the input at the optimal level.
All right, thank you. Let's see, this next one is for you, Stefan, but there are a lot of questions of similar flavor that have come in, so I'm going to see if all of you want to answer it after Stefan. But it's, what's the incentive for the average smartphone user to download and use an app to contribute to the crowdsourcing of this data?
Mm-hmm. Well, I think the direct incentive could be that it can protect yourself. So you would yourself also notice that you're being jammed, and you could also get warnings if there is a jamming event nearby, if that one would be part of such a network. On the other hand, is also, besides the personal advantage, of course, you're helping the community. I think it's just a not direct incentive for you personally, but I think all of us have interest that the spread of jammers is kind of kept low. And finally, maybe someone has a clever idea to maybe write a game app that gives you a high score if you're finding a jammer or something. I don't know. But it's essentially, it's a good question. And I think besides the personal protection, I think there's actually little benefit besides helping the community to fight jammers.
right. Sherman or Frank, do you want to add to that about the incentive?
Well, yeah, I thought that was well put by Stefan. I just say that helping the community is helping yourself, because you'd want there to be a mechanism to remove jammers, so that, and if there is, things will work better for you. And well, maybe not the only way, but one way to do that is to have crowdsourced and crowdsourced location of jammers. And if you participate, then you're helping the community and yourself both at the same time.
Sherman, do you want to add to that, or do you think it's been covered?
I think it's both well said. I think the one thing that kind of Frank hinted at in his talk is that we should make if they're helping, we should try to make these apps as low resource intensive as possible, and that way they can when they're helping, they don't feel like they're being burdened by helping. But again, the incentive is really to help the community, and if we can make it as transparent, as easy as possible, and protect privacy, that would just make it a no-cost solution for them.
Yeah, so I'd like to add to that as I mentioned in my last slide, it's possible to make apps that do this with no impact on power, because you can make the app so that it's only running when something else is using the GNSS receiver in any case. And then that seems like a natural thing, in that you as a user only need to know about jamming when you're actually using GNSS. And when you're actually using GNSS, if some monitoring app is then invoked, it then automatically listens in and turns on the monitoring, then you get the benefit without it costing you anything, because your GNSS receiver is on in any case. And in terms of privacy, even an app that's listening in passive mode still has to get permission, and in terms of location, it can be sharing the location of the jammer, but none of your personal information is attached to that. So there's anonymous locations that's the only extent of anything that you're sharing if you participate.
All right. So while I have you on, Frank, the next question I'll direct it at you, and it's a question about, can carrier phase cycle slip detection be added as another Android indicator of jamming? Many mobile device chipsets track L1 carrier phase and provide an indication of cycle slips. So what's your thought on that?
So yes, good question. And if anyone's interested in carrier phase, if you just go to those pages that I pointed out and look for the keyword carrier phase, you'll find it. A couple of things to point out while we're discussing it. The carrier phase field itself has been deprecated, and it means it'll disappear eventually, and it's been replaced by something called accumulated delta range, which is a different way of measuring the same thing. And that field is very sensitive. So the slightest thing, like if you bump a phone, for example, you can cause there to be a cycle slip. So it's much more sensitive to any kind of interference, including RF interference, than CN0 or the AGC. So in that way, it might be a good addition, because maybe you've got a phone that's just sitting there somewhere and is not being moved around very much, and as long as it's out in the open, you might get good carrier phase, and cycle slips would be something like an early warning of some kind of jamming. So I think it's you could use it. It's a good idea, but should not replace the use of the AGC. It should be in addition to it, and view it as something that's fairly easy. Carrier phase is fairly easy to get cycle slips, so it's kind of a very high sensitive detector of any interference.
Right. Let's see, Sherman, this one is for you, and it had to do, I guess you did show some results about aircraft, and the question is there an altitude at which, above which aircraft are going to be immune to jammers, or is it still an issue for aircraft flying at high altitudes, I guess, is the upshot of the question.
All right, thanks, Tim. Generally, from the PPD devices, no, but I think, I've seen with the data from the Eurocontrol presented, when you have people using high-power jammers, as you might expect over a war zone like Syria, that can affect aircraft at higher altitudes. So that's the extent that I know of, but I would assume that it really just depends on what your jamming threat is. PPDs aren't meant to go very high, but unfortunately, they can affect the most important part of the flight operation, which is the landing portion.
Right. Let's see. Next question. Let's see. This one is for you, Frank, it's a question about why not just add this as an experimental feature to Google Maps instead of making a dedicated app for it? Is there what are the trade-offs there?
Okay, good question. Firstly, I think it's fairly early days for all of this. As you saw, there's only a few phones that support the AGC, and also, as you see, we're just beginning to experiment with these ideas of, we're at the stage of testing, showing some things against a microwave oven and so on. So it's fairly early days of using these different measurements to detect jamming. So it seems appropriate to us to make these measurements available to the developer community so people can experiment in different ways. And that's kind of where we're at with this thing. Generally, some supporting this inside of a Google app itself would happen when these measurements are much more widely available. And then also Google Maps is just one location app. We'd probably want to have some kind of detection that covers all uses of location, including other apps. But I guess the summary of the answer is early stage. We want to support the GNSS developer community to see what they can do. We believe that the whole community together is smarter than we are on our own, and then we'll see how this develops from here.
Thanks. Sherman, this one is for you, and it has to do with, basically the question is, can things like cell towers and other fixed infrastructure be used as a network of monitoring stations for this kind of an application? What are the issues? What are the trades? Anything you want to say on that?
Sure. So I absolutely do believe that these fixed infrastructure pieces and even Internet of Things devices can be used to monitor anything that's built in with a GPS that's running, that can provide these measurements. I think can be considered usable. Again, we have to worry about how trustworthy, how reliable these measurements are. Certainly, if it's operated from a cell tower that's operated by an operator that's a different trust level than something that might be put in, an IoT device that might be put in somebody's home, because a malicious party might add such a device to the network to provide false information. And so there are some concerns to using that, but I think that generally, like with crowdsourced smartphones, we can use them. And in fact, since they're static and presumably a little better controlled, we have better usage of their measurements.
All right, thanks, Sherman. Let's see. Next question. This one is for you, Stefan. It's a question that it's actually partly I'm thinking about it as well. Is so as this data rolls into these from these apps into your network, the place where the data is concentrated. How long does it take to really give out an answer that something is that there's a jamming and that there's interference going on? Is it instantaneous? There's a lot of data have to come in. How does all this work?
Mm-hmm. I could imagine that it could be almost instantaneous. So it depends essentially on the amount of data. So if 20 different smartphones are reporting a jamming incident more or less at the same time, then this could immediately cause a jamming alert message within a few seconds delay maybe. On the other hand, if you only receive a single report from one smartphone, then you might not immediately want to trigger an alert, because it could be someone holding the phone next to a microwave oven. So I think it depends on the one hand how many reports you receive, and on the other hand, what is your acceptance of false alarms. But technically, I think it could be nearly instantaneous.
Sherman and Frank, do you want to say something about that?
So yes, I just agree with what Stefan said at the end there. For detecting jamming in your own device, it's instantaneous, as you saw with those experiments with the microwave oven. But to know that there's a jammer around is going to require there to be a community of people, and then there of course will be some delay, and it depends on how many people. But I would expect it to be order of a few seconds.
Right. Sure,
Nothing to add.
Okay, nothing to add. All right.
Give this comment.
All right. Well, so this next question is going to be for you, Sherman. So we've talked a lot about jamming and interference. Do you think that any of these methods can be used for spoof detection?
So thanks so much. Yeah, so can these methods be used for spoof detection? We have been looking at smartphone measurements for spoof detection and localization, and we believe, well, certainly the different measurements provided by the phone can be used for a spoof detection. So we've looked at the AGC, the seed and not to look at to determine whether we have interference, jamming, or spoofing, because they have different characteristics in that domain. We've looked at other measurements. You know, Frank talked about fuse positions, so we can look at that if there's some very gross spoof detection methods. And then looking across multiple smartphones, we can look at, you know, there are correlated changes in location or location data, such as pseudo ranges. We can use that also for spoof detection. So I would say that some of the techniques can be adapted to spoof detection, but we'll look at, but really we'll also look at different sets of data that's available at the phone to do spoof detection, because it has, you know, jamming affects the phone differently than spoofing.
All right. Let's see. Next one for you, Frank. How well can you localize a jammer using AGC levels, considering the resolution of the AGC measurements?
So the answer is we don't know. What we do know is that the resolution of the AGC measurements is coarse, as you've seen, and it will vary depending on the manufacturer of the GNSS chip. So you should view the AGC as something that can tell you if you're being jammed or not. The actual levels themselves may not be very meaningful. I doubt you could infer much from the level of the AGC, because one phone may say AGC minus 15 dB and another one may say minus 20, but if those are different models of GNSS receiver, they may mean different things. The one that's reporting minus 15 may actually be experiencing more jamming than one reporting minus 20, depending on how that AGC works. So you should view it as something that tells you in a binary way per phone if you're being jammed. And then how well can you localize? Well, it's just a question of how strong is the jammer, so how far away could it possibly be, and how many people are participating in some kind of crowdsourcing. So I would guess the best you're going to do is a few tens of meters if you had a good crowd of people participating in trying to locate a jammer.
Okay. Well, while I've got you here, let me ask you another follow-on, a question, but also I want to hear from Stefan after Frank. And it's basically, how difficult would it be to use the existing GNSS network of receivers, say in a telecom network, for this kind of an application?
So who do you want first on this?
Well, Frank, you go first because you're online here, and then I'll see if Stefan has something to add to it.
Okay, great. I think this is a nice follow-on question to what I just answered. So from a technical point of view, if you are the person who owns those receivers or owns that network, then it's not difficult at all. And there's some definite pros of dealing with a reference receiver. You'd probably know, well, for sure you would know what kind of receiver you're dealing with, so you don't have this issue of there being different manufacturers giving different results. So the value of the AGC itself could be much more useful. On the other hand, there may be far fewer network receivers in a network, so in terms of localizing a jammer, maybe they couldn't get such accuracy. On the other hand, the network owner owns all those receivers, so they don't have to wait for people to opt in. So you see, I think it would be fairly simple for the network operator to do this. It would have some nice complementary characteristics compared to crowdsourcing, and it's really up to the telecom operators themselves to do such a thing, and to it's easy for me to say it's easy, but it's really up to them to say how easy it would be for them. But technically, I think it's quite straightforward.
It looks like, well, unfortunately, I'm going to give you a chance, Stefan, because it looks like we just ran over time here. But again, it was a nice discussion.
Nothing to add to Frank's response. Yeah.
But with that, I'm going to thanks for all the questions, and I'm going to hand it back to Lori here to say some final words about before closing off this webinar.
All right. Well, thank you. And folks, before we sign off, would like to thank each of you for joining us and trust you found today to be of value. Special thanks to our distinguished panel members and, of course, our sponsors and co-hosts, Rody and Schwartz and InsideGNSS. Again, thanks for joining. This is Lori Dearman saying, hope we see you on the next one. Bye for now.